All right, so in the last lesson, we managed to convert a 2D touch on the screen of the iPad or the iPhone and convert it using a hit test to a 3D location in the real world. And then we created this function called add.dot to add a node onto the 3D world to show where we tapped. Now, in this lesson, I want to get into the meat of this application, which is really calculating the distance between dot nodes that we place onto the scene. So the first thing I'm going to do is I'm going to create a new variable that is called dot nodes. And this is going to be an array of scene node objects. And I'm going to initialize it to an empty array. So this is an array that I'm going to use to keep track of all the dot nodes that we put onto the scene. So down here where we add new dot nodes into the scene, every single time I add a new dot node, I'm also going to add it into my array of dot nodes. So I can see that the naming is a little bit ambiguous, but basically the plural, which is dot nodes, is the array, and I'm going to append the dot node that gets created whenever we tap on a new position. So the singular is the scene node and the plural is the array. So feel free to change that naming however you want, whatever makes sense to you. And then once we do that, we're going to check if there are 2 or more dot nodes in the array. So I'm going to say if dot nodes dot count is greater than or equal to 2, then I'm going to call a function called calculate. And calculate doesn't exist yet, so I'm going to go and create it. And this calculate function does not take any inputs, but it does have a functionality. The first thing I want to specify is I want to create a constant called start that is set to equal to the first object in the array of dot nodes. So that's going to be dot nodes square brackets 0. And that's going to be the first dot that we put onto the scene. So that's our starting position where we want to start measuring from. And then I'm going to create another constant called end. And you guessed it, this is going to be the second dot that we place on the screen, which is the ending position of where we want to measure. So we're measuring the distance from the start to the end, and we've got these 2 dot nodes that each have a 3D position, and we're going to figure out the distance between them in 3D. So the first thing I want to do is I want to print to the console the start and end positions so that we can have a look at what they look like and code accordingly. So I'm going to print start position and end position, and let's give it a go. All right, so we've got our feature point detection, and I'm going to put down 1 dot here, and then I'm going to put down another one on the opposite side of my keyboard. Now, if we have a look inside our console, you can see that we've got 2 scene vectors printed in here. And if I zoom in, you can see that this is the start position. So it has an X, a Y, and a Z position. And then this is the end. X, Y, and Z. So the next thing we need to do is simply figure out the distance between these 2 3D coordinates. So I think it's a little bit difficult to imagine these coordinates in 3D space just by looking at the numbers. So let's head over to a 3D graph maker to try and plot this in 3D. So the first thing that I'm going to do is to show and hide grids. So at the moment, we've got a grid on this 3D graph for the X and Y 2D space, but that is not the same as what we have in ARKit. As you know, it's the X and Z grid that we need. So let's enable that and disable that one. So as you can see on our graph, as Y goes towards the positive, that's going up in 3D space. And as X goes towards the positive, that's going towards the right in 3D space. And as Z goes towards the negative, that's going forwards in our 3D space. So now we've got this more or less aligned. I'm going to go and put those 2 3D positions that we got back. So the first one was the start. So I'm going to add a point here. And X is equal to, I'm going to multiply this by 100 to make it a little bit more obvious on this graph. So X was equal to 6 point something, Y is equal to minus 20 point something, and Z is equal to minus 13 point something. So let's go ahead and adjust that. So these are basically the same numbers as you see over here, just multiplied by 100 so that we see it a little bit more clearly on the graph. Now that's our first spot done, and you can see it's down there. Now the next thing I'm going to do is plot the second spot. So this is the end position. And again, we're going to keep it on the same scale. So we're going to be multiplying these values by 100. So this one's going to turn into a minus 20 point something. 20.6 something, 20.06. And y is going to be minus 21. And z is going to be minus 5.6. All right, cool. So let's go ahead and add our second spot on here. So we can now see them on the scene. So you can see that the y positions of both of these points are more or less along the same plane. And that's because we tapped on two spaces on the keyboard, which is more or less on the same plane as each other because they're both on my keyboard. Now, the reason why it's so far down in the y position is because the y position here is relative to the position of the camera. So if the position of my camera is at 0y, then my keyboard is just a bit below it. So about, what is that, 20 centimeters below? So the next thing that you'll realize is that this point in 3D has a x component and a z component. So we need to figure out this distance here from A to B. Now, how do we do that? Well, this is where high school maths is going to come in really handy. So when we did high school maths, you would have learned about something called Pythagoras' theorem. So this is where in a right-sided triangle, so this is 90 degrees, the hypotenuse, so this line here, we can find out its length if we know the length of A and the length of B. Let's call this h. And h is going to be equal to the square root of a squared plus b squared. So depending on how long ago that was, it might take a little bit of jogging of your memory. But the point being that if we wanted to figure out a distance between 2 points in 2D space, it's as simple as working out the root of the square of these two sides. So this is in 2D. Now, the problem is that our coordinates are more or less in 3D. And in order to figure out the distance between two coordinates in 3D, it's a little bit more involved. So let's say here that we've got this 3D space, right? So we've got a point here and a point here, and we want to work out this distance here. Now, in order to figure out that distance, we need A, B, and C, which we have because that corresponds to the difference between our X, our Y, and our Z positions. So if this is our starting point and this was our ending point, we're trying to figure out the distance between the two in this 3D space. And in order to do that, we're going to use a slight variant of Pythagoras' theorem. And the equation basically assumes that you know what A, B, and C are. And once you do, then the distance between these 2 points in 3D space, so let's call it distance D, equals a squared plus b squared plus c squared, and then the entire result rooted. So taking those coordinates that we saw on screen, where we've got x1, y1, and z1, right? So that's the starting position. And then down here, we've got x2, y2, and z2. And that's the ending position. So now we can use the starting and end coordinates to figure out A, B, and C. And if you imagine this being 3D space, this axis is the x-axis, this is going to be y, and that is going to be z. So now to work out A, B, and C. So A is going to equal x2 minus x1, and that's the distance of A. B is going to be equal to y2 minus y1, And then C is going to be equal to Z2 minus Z1. And once we've got A, B, and C, then we can use the Pythagoras equation to work out this distance D, using D equals A squared plus B squared plus C squared, and then the entire thing square rooted. All right, so that's a little bit of math. The code will still work if you believe Pythagoras or not. And if you ever need to work out the distance in 3D, then this is simply the equation that you need to know. All right, so let's head back into our code and go and implement those things. So inside calculate, we know that the distance is equal to the root of x2 minus x1 to the power of 2 plus y2 minus y1 to the power of 2, and then finally added onto that is z2 minus z1 again to the power of 2. So now we need to convert this equation into Swift code. So I'm going to make my code a little bit more wordy just so that you can see what is happening. So let's say let A equals the distance on the x-axis. So we're going to take the end dot position dot x and we're going to subtract the start dot position dot x. And then B is going to be equal to end position dot y minus start position dot y, and C is going to be end position dot z minus start position dot z. Okay, so now we have A, B, and C, and to work out the distance, all we need to do is say let distance equals square root. So this is a function that is available to you through UIKit. And inside this square root, we're going to give it a double. And the double is going to be equal to power. So we're going to use the power function, which takes two values. So first is going to be A, the value, and then the second one is the power, the exponent. So in this case, it'll be 2. So we're basically saying raise A to the power of 2. And then we're going to add to this same thing, power B 2, and finally power C 2. So now we've converted this formula into a 4-step process. Now, if you want to, you can make this more succinct by simply putting this in here and putting this one in here instead of B, and C can be substituted as well, and you can get rid of all of that. Now, it's completely up to you. If you find this too confusing, then go with the original, but otherwise this should work. And I've got an extra comma in there, so I should get rid of that and it should work. Remember that you can actually format your code so that you can see more easily what's actually happening at a glance. So I think this is a slightly easier way of seeing what's going on rather than that gobbledygook. All right, cool. So the last thing that we're going to do is we're going to print the absolute value of our distance. So by putting our distance inside this function called absolute, we basically remove any signs in front of this distance. So if distance happened to be negative, then this will still change it into positive. So basically we're ignoring the sign by using ABS or absolute. Because we don't know if the end is, more positive than the start, or whether the start is more positive than the end, it doesn't really matter for us because all we care about is the distance. So I'm just removing any negative signs in front of the distance. And now if we give it a spin, we should be able to see our distance on screen. All right, so that was 0.27, so that's 27 centimeters. And if you measure your own MacBook Pro, you'll see that the distance from one side to the other side of the keyboard is about the same. So awesome. All that high school maths is finally useful for something. All right, so in the next lesson, I'm going to be teaching you how to render or how to create 3D text in our AR scene so that we'll be able to show this distance that we've detected in the same scene where the user is asking for the distance. So we can show a 3D text of the distance between the 2 points inside our app. So I'll see you there.